Okay, welcome to Let's Get to the Marks. Going through the GCSE Chemistry Higher Tier. This is the Paper 2 AQA from 2019. What I reckon you do, it's an hour and 45 minutes. We ain't going to take that long going through it. But what I suggest you do is you read through the question, have a go with a pen and paper, make the revision active, best way to learn, and then unpause and watch the explanation for each question. So this question is about crude oil and hydrocarbons. Figure 1 shows a fractionating column used to separate crude oil into fractions. Table 1 gives information about some of the fractions. So you've got petrol, kerosene, diesel oil, etc. here and their boiling points. 1.1 suggests a suitable temperature for the furnace in figure 1. Why don't you pause the video, have a go now. All right, I'm going to go through it. So you see the crude oils coming in the furnace. We want it to vaporize, to evaporate. And we can see that bitumen vaporizes at 450. So if you want it all to vaporize, you want it to be like 500, something like that, above 450. Yeah, I mean, really, you just need the heavy fuel oil to vaporize because the bitumen comes off as a liquid. Explain why diesel oil collects above heavy fuel oil but below kerosene in the fractionating column. So this has got a complicated explanation that they're not looking for, and then a simple explanation based on the evidence in Table 1. And they specifically put Table 1 in dark black, so they want you to look at Table 1 and use that. Now, if I wanted to do the complicated method, I would say diesel oil is a small molecule, smaller than heavy fuel oil. However, it contains longer molecules than kerosene. And smaller fractions, smaller molecules condense higher up the tower because they have weaker intermolecular forces that are easy to break, so they have lower boiling points. Now, that's all very, very long and detailed explanation, and we actually don't need that to get the marks. The simple marks are that diesel oil condenses higher than heavy fuel oil because it has a lower boiling point than fuel oil. So diesel oil has a lower boiling point than heavy fuel oil, but it has a higher boiling point than kerosene. So kerosene is the lowest boiling point, hence it comes out the furthest up the tower. The lower your boiling point, the higher up the tower you come out. Okay, the bit in blue was the correct answer to put there. I just thought I'd put an extra deep explanation. 1.3 suggests 2 reasons why bitumen's not used as a fuel. Pause the video, have a go. Okay, so what do you want from a good fuel? Think about petrol in your car. Think about the gas in your Bunsen burner when you're lighting it at school. What things should a fuel have? Well, bitumen is a thick black substance that we roll out on roads to smooth them out. You've probably seen it. Um, it's very thick and difficult to pour and use, and also it doesn't light easy. It's very hard. You couldn't just throw a match on bitumen and it would catch a light. It's not flammable. So there are 2 reasons why bitumen is not a good fuel. Okay, let's move on to 1.4. Get 2 marks for this one. And don't forget to hit the like, peoples. So yeah, bitumen down here. This is the one. It's not very flammable. It's dark, it's thick, and it's found at the bottom. And it has a high boiling point. Ones with a low boiling point, like petroleum gases that come out your Bunsen burner. So the higher up you go, the lighter in color the fuels become, the more flammable they become, and the less thick, the less viscous. So petrol contains mainly alkanes. Which of the following compounds is an alkane? Now, you need to know this off by heart. This is the general formula for alkane, CnH2n plus 2. And it means if you know the carbons, say the carbons are 2, then to find the hydrogens, you times 2, add 2. So if you have 2 carbons and you're an alkane, you're going to be ethane, and you're going to have 6 hydrogens. So the first one's wrong because it's only C2H4. The second one, C4, you should times 2, add 2. So we go times 2 is 8, add 2 is 10. And of course, you can see there that says C4H8. That's wrong. C4H10 is butane. It's an alkane. Let's look at the third one. The third one is C6H14. And if you go times 2, 12, plus 2 is 14. Hexane, that's correct. And so that one is an alkane because if you take the carbons and you times 2, add 2, you get the correct amount of hydrogens in an alkane. You can see the one at the bottom. They haven't done that. Right, large hydrocarbon molecules in the diesel oil fraction are cracked to produce smaller hydrocarbon molecules. Describe the conditions needed to crack hydrocarbons from diesel oil. Oh, from a diesel oil fraction. How can you make a bigger fraction into smaller fractions? We call it cracking, and you need a catalyst. So that's one of the conditions you need is a catalyst. Now, there are about 6 catalysts you can name for cracking, but the one is alumina or aluminium oxide, also known as Al2O3 if you use the formula. And you can use silica, which is silicon dioxide, SiO2. And of course, another condition is that we need a very high temperature, I can't remember the temperature, guys, but it's something like 450 degrees. But you'll probably just very high temperature will get you the marks in a mark scheme. 1.6, explain why large hydrocarbon molecules in the diesel oil fraction are cracked. So why do we take big molecules like diesel and crack it to make smaller ones like petrol, kerosene, or petroleum gases? And the idea is that the smaller hydrocarbons are better fuels. They light more easily, they burn better, and so they're better fuels. They're in higher demand. All the countries around the world need petrol for cars and for lorries and kerosene for aeroplanes. So the smaller fuels are in big demand, which makes them more valuable. It's all about supply and demand. So cracking big hydrocarbons makes them more valuable, smaller hydrocarbons. Also, when you do cracking, you get things called alkenes that have a double bond, and alkenes can be used to make plastics, polymers with addition polymerization. So that's another use. Right, complete the equation for cracking, C15H32. Now you can see the conservation of mass. Everything on the left of the arrow has to equal everything on the right. So we just subtract C12H26 from C15H32, and you're going to be left with C3H6, and that is an alkene because it has the general formula CnH2n, and that is going to have a double bond, hence why it's missing two hydrogens. When you have a double bond, you have less hydrogen. So C3H6 is propene. Question 2. This question is about lithium carbonate. Lithium carbonate is used in medicines. Figure 2 shows a tablet containing lithium carbonate. 2.1. Lithium carbonate contains lithium ions and carbonate ions. A student tested the tablet for lithium ions and for carbonate ions. The student used a metal wire, dilute hydrochloric acid, lime water. Plan an investigation to show the presence of lithium and carbonate ions in the tablet. You should include the results of the tests for the ions. It's worth 6 marks. They want you to show how you could test for lithium ions, what's the test for carbonate ions, and what is the positive result, and it's worth 6 marks. Pause the video, grab your pen, grab some scrap paper, have a go, and then unpause and watch me go through the answers. Okay, now the first thing you could do is there's 2 options here. You could dissolve the tablet in water. Most carbonates don't dissolve, but lithium and sodium carbonate do dissolve. So you could just dissolve it in water and that would free up the ions, so the ions are free to move, your Li plus and your CO32 minus ions. Or you could react it, you could dissolve it in acid. It's going to form a salt and water, so you're going to get lithium ions knocking about there as well. Personally, I just dissolve it in water. I wouldn't do that. Just dissolve in water, and it will contain lithium and carbonate ions. Now wash your metal wire because it might have some other ions like sodium ions or potassium ions already on it, which will mess up your test when you stick it in the flame. It will make your results not valid because it will confuse the color. So wash the metal wire with distilled water, then dip it in hydrochloric acid, evaporate the acid in the hottest part, the middle of the Bunsen burner flame. That will clean the wire. Now it's totally free of other ions. Dip the metal wire into the solution, which contains lithium ions. Hold it in the non-luminous part of the Bunsen burner flame. That means don't put it in the yellow part, don't put it in the bright blue part, put it in the colorless part of the flame, and it will glow with a red flame. The better word to use is crimson, like blood red or crimson red, which is like the color of blood, a deep red. And that will tell you that you have lithium ions. So we now need to explain the test for carbonate ions. Well, you could react with acid. So take the carbonate part of the tablet, crush it, drop it into an acid. When you mix the carbonate ions or the tablet with the acid, you're going to see bubbles. And those bubbles are going to be carbon dioxide gas. Now, you could potentially just say, drop the tablet in acid, you'll see bubbles. That proves there's a gas. But it doesn't tell you it's carbon dioxide because it could be hydrogen. So to prove it's carbon dioxide, you use lime water. You could dip a stirring rod in lime water so there's a drip on the end, hold it above your beaker. The gas as it comes up will turn the lime water cloudy. Or you could use a gas syringe with a delivery tube into a test tube of lime water, and that would turn the lime water cloudy. And there you go. You get all your fat 6 marks like that. The only bit I'd probably change from my answer here is I wouldn't bother reacting with acid at the start, because you'll get rid of all your carbon dioxide at the start. You might as well dissolve it in water first, then save a bit of the tablet for crushing and chucking in the acid to prove that carbon dioxide is released. And here's the equation. Lithium carbonate plus hydrochloric acid goes to lithium chloride your naming salts bit, plus water, plus carbon dioxide. So I'd probably just dissolve it in water first to free up the lithium ion. So you can do the lithium ion test with the Bunsen burner, the first part. And then I would put some of my tablet in acid after to release the carbon dioxide from the carbonate, and you can test that. All right, cool. That's 2.1 done, and that was worth 6 marks. Let's do 2.2. The tablet also contains other substances. The substances in the tablet are present in fixed amounts. What's the name? Given to a mixture like this. So here's the key bit you need to know on your revision cards. Mixtures that contain fixed amounts, specific amounts, are known as a formulation. Spelt that wrong, so I don't know what I called that, a formulation. So let's change that again. It's a formulation. Something like paint, perfume, um, deodorant. They have different chemicals put together, one to bind the chemicals together, one to give a lovely smell, one to make them last a long time. They have a specific amount of each chemical put together for a purpose. That's called a formulation. A tablet has a mass of 1.2 grams and contains 700 milligrams of lithium carbonate. Calculate the percentage by mass of lithium carbonate in this tablet. First thing to do, I need to make my grams. I need to make everything into grams or everything into milligrams. You choose, but you need to put the two masses in the same because they're in different units right now. So I'm going to turn the milligrams into grams by going 700 divided by 1,000. 700 milligrams, 700 thousandth of a gram is zero 0.7 grams. So I've got 0.7 grams of Li2CO3, lithium carbonate, and I have a 1.2 gram tablet. How much of that lithium carbonate, how much of the tablet is made of lithium carbonate? You do 0.7 over 1.2 times 100 to work out the percentage of the 1.2 tablet that is lithium carbonate. Now we know that half of 1.2 is 0.6, so we know it's over 50%. And if you do 0.7 divided by 1.2 times 100, you get 58.3%, something like that. They'll probably give it to you just rounding it to 58%, to be honest. And that will get you 3 fat marks. Lovely jubbly. Okay, we're on to question 3. This question is about the rate of reaction. A student investigated the rate of reaction between magnesium and dilute hydrochloric acid. The equation is MgS 2HClAq MgCl2Aq plus H2G. Which state symbol in the equation for the reaction does not represent the 3 states of matter? Now you know what the 3 states of matter are. Pause the video, have a go. Which one is not one of the 3 states of matter? So the 3 states of matter are solid, liquid, gas. Oh my gosh, look how I spell aqueous. It's AQU, you dipstick. So AQ is aqueous. It means dissolved in water. So it's not one of the solid, liquid or gas. It's not one of the states of matter. What 2 pieces of measuring apparatus could the student use to find the rate of the production of hydrogen gas? Now think about the word rate, R-A-T-E. It means speed. Pause the video, have a go at this one. Okay, so if you wanted to measure the speed of something, what 2 things would you need? Now we know if you're doing physics, speed is distance over time. Rate, R-A-T-E, speed is always measured over time. In this situation, it would be volume of gas or number of bubbles over time. So if we want to do the volume of gas, we're going to use a gas syringe or a measuring cylinder to catch the gas and measure the volume. And then we need a stopwatch, a timer, etc. to work out the time in seconds. So you normally do volume of gas, centimeter cubed over time. Okay, we've got a little graph. Wunderbar. Not. Table 2 shows the results of this investigation. We've got time in seconds, and that is the x-axis. And then on the y-axis, we've got rate of production in gas in centimeter cubed. Don't forget that the y-axis is always the dependent variable, what you measure, and the x-axis is like what you're changing. So plot the data from table 2 on figure 3. You should draw a line of best fit. So this is a case of just going 10 and 6.9, 20 seconds along the bottom and up to 3.9, then 40 and 0.9. So that should just be below the 2. That was not a good effort. When, oh no, 30 and 2 and 40 and 0.9 is just below there. And then 50 and 0.3, that's going to be 1.5 squares up. Each square, baby square on the y-axis is worth 2 here. And 60 seconds, we're at 0. Now I need to do a line of best fit. Oh my gosh, I ain't looking forward to this. Here we go. That's all. Got a squiggle, got a squiggle. Now it's supposed to be done one smooth curve. So if I did it like that, I'd have to leave it like that. But that is not very good because I've not hit all the points. It's very hard if you're not doing a pencil with a graph. Oh my gosh, I missed it again. Oh my gosh, Mr. Floppage. this is becoming ridiculous. Let's try again. Okay, a little bit better. This is going to have to do, folks. You're not allowed to go back and forth. It has to be one go, just one go at it with a straight line. And this time I'm doing a curve because there is a natural curve to the plots. If there's a natural curve to the plots, it's a curve rather than a straight line. Give 3 conclusions that can be drawn about the rate of reaction between magnesium and dilute hydrochloric acid from this investigation. Use the graph and the table. So let's put my line back on. What 3 conclusions can we make about the results? And they've asked you to use the table. So what 3 things can you say from the table? Well, as the time goes up, what happens to the rate? We can see as time increases from 10 to 60 seconds, the rate decreases from 6.9 to 0. So that is your first conclusion. As time increases, rate decreases. And I can bust out the numbers and say at 10 seconds it was 6.9, at 60 it was 0.0. That's going to get you the marks because you're using the information in the table. And that's a nice conclusion. What's another conclusion I can make? When is it decreasing the most? Look between 10 and 20 seconds. Now, there's loads of different points you can make here, but I'm going between 10 and 20 seconds, it's decreased by 3. And then if you look at another like 40 to 50 seconds, it's decreased by 0.6. So the biggest rate of decrease is between 10 and 20 seconds. It's the steepest part of our curve. You can see there right at the start, there's a very steep part to the curve on the graph. And so we can see the rate of decrease, the reaction is slowing up later on. It's not decreasing as fast. There's less particles, less collisions going on. We've got less reactants left later on. So there's less collisions. The rate of reaction is decreased. So, and now I would go down to where it's 0. Look where it's 0, the rate of reaction. I know the rate of reaction. Another conclusion I can say, the rate of reaction has stopped at 60 because it is 0. However, I can be a little bit more clever than that and say the rate of reaction stops somewhere between 50 and 60 seconds. I don't know exactly where, but somewhere between 50 and 60, it hits 0. Maybe at 51, it would have got to 0. We don't know because we haven't got results for 51, 52, 53. But we definitely know between 50 and 60, the rate of reaction stopped. Okay, those are my 3 conclusions over here, people. Right, let's check out the last part to this question. What's this? 3.5. The student repeated the investigation using dilute hydrochloric acid at a higher temperature. So they're using a higher temperature. All the other variables are kept the same. Which 2 statements are correct? More bubbles were produced in the first 10 seconds. Yes. Higher temperature, what are the particles doing? They have more kinetic energy. They're moving around more, bumping into each other more. So the reaction is going to happen faster. Are you going to get, the second one says the activation energy for the reaction was higher. No, you don't change. The only thing that changes the activation energy is a catalyst, and it would lower the activation energy. It wouldn't make it higher. It would lower it. The magnesium was used up more quickly. The reaction finished at the same time. The total volume of gas collected was greater. It's actually going to be that the reaction happened more quickly. It was finished faster because you've got the same amount of particles, but they're bumping together more quickly, so it'll be over faster. The total volume of gas collected was greater. No, that's not true. In order to increase the total volume of gas, you'd need more magnesium or more acid particles, but they use the same amount. So you can't make more if you don't have more ingredients. There we go. And the reaction finished at the same time. No, we just said it finished more quickly because it's at a higher temperature. So it's going to be over more quickly. It'll reach 0 first. And that's the end of the question. Bloop. Okay, a student investigated the rusting of iron. This is the method used. Set up the test tubes as shown in figure 4. Leave the test tubes for 1 week. Examine the nails for signs of rust. So we've got test tube 1. They've stuck an iron nail in a test tube of water. Test tube 2, we've got a rubber stopper with an iron nail in some dry air. And test tube 3, we've got oil on top of boiled water with an iron nail. And test tube 4, gosh, there's 5 of these. We've got a painted iron nail and we've got water. And then test tube 5, we've got stainless steel nail and we've got water and obviously exposed to air as well. Explain what would happen to the nails in each of the test tubes. So you need to say whether it would rust or not rust, and then why. And you need to do that for test tube 1, 2, 3, 4, and 5. So 5 sentences, 5 marks. Why don't you press pause on the video, have a go, and then unpause and watch my explanation. All right, let's go, let's go, let's go. So I'm going to go through it. Look at test tube one. We've got water, we've got an iron nail, and we've got air. Now, test tube one, guess what would happen? It would react. I'm going to put T1, iron nail rusts as exposed to air and water. So the first one we've got, it's going to rust because it's got air and water. It's going to oxidize and become iron oxide. Okay, let's go T2. The iron nail, dry air, no water, wouldn't rust. No rust as no water in dry air. Oh my gosh. No water in dry air. You could try it with normal air that hasn't been dried, and you might find it still rust because there's water vapor in the air, on a cold day when you see your breath coming out. So let's have a look. T3. Okay, here we've got water and we've got the iron nail, but there's a layer, I can't speak, of oil on top of the water. That prevents oxygen. Oxygen can't actually get O2 cannot get in there past the oil. Also, the boiling of the water forces any oxygen out of the water. So this water doesn't have pockets of oxygen bubbles hidden in within it because it's been boiled. And yeah, there we go. So T3 is why you shouldn't reboil the kettle when you're making tea because there's no oxygen in it and the tea doesn't taste as good if you keep using the same reboiled water. Okay, anywho, enough of rubbish like that. Oil prevents oxygen reaching the nail. No oxygen in the water as been has been boiled, so cannot be oxidized, no rust. So essentially, I've longed that out a little bit. Oh my God. What are my days? T4 peeps. Test tube 4, they've painted the iron nail here. That nail is in contact with oxygen and water, so it should rust, but the paint provides a barrier. We call it, it's a protective barrier. So paint provides a barrier. Sorry about any typos here. I've got an extra I in provides. It's like provides. Paint provides a barrier, stops water and air contacting nail, so no rust. Jeez. Let's do T5. The final one, I'm running out of room. T5, stainless steel nail. Now, this again is in contact with the air in the water, but it won't rust. Stainless steel contains an element called chromium, is an alloy. So steel, oh my days, what's happened there? Right, something weird up in there. Steel, oh my gosh, what's going on? Steel is an alloy. I don't think you need to know that steel has chromium. Um, will not rust. So it does contain iron. Steel is an alloy of iron, but it's not going to rust because it contains chromium, and that prevents the properties of alloys aren't the same as the metals within them. So it has that steel. Stainless steel is actually carbon, iron, and chromium. Chromium. Oh my God, I can't. I've lost the ability to speak. There's 5 points there, peeps, but I've tried to cram it in. No, diddy. Bish, bash, bosh. 5. Let's move on. That was 4.1. Let's go to 4.2. Magnesium is fixed to some steel ships. Explain how this prevents it from rusting. So I'm going to do you a little diagram. Why don't you bust out your pen and paper, have a go, and then yeah, unpause and watch the explanation. So here's your ship, right? Kind of looks like a sailing boat, does it? Maybe not. What happens is oxygen and water react with iron in the hull of the ship. You call the metal bit in the ship the hull, and they will oxidize it to that orange flaky rust, and it means you're going to get holes and your ship's going to sink. And steel contains iron. If it's not stainless steel, then this stuff is going to rust and it's going to sink. So how does nailing on block blocks of magnesium to the hull of a ship, and they often use zinc rather than magnesium, but you could use magnesium. So how does nailing on metal blocks on the hull below the waterline prevent it rusting? Well, magnesium is more reactive than iron, and so reacts with the oxygen in the water instead, sacrificing itself and allowing the iron to remain unreacted and strong. So what we want to say is magnesium is excuse any typos, more reactive than iron. So the magnesium reacts with the iron instead. Uh, no, reacts with the oxygen and the water instead. Yeah, magnesium. Oh, look at this. Look at the spelling, peeps. It's disgusting. Magnesium is more reactive than iron, so magnesium reacts with the oxygen in the water instead, um, leaving the steel with no rust. So protects it, basically, is offering protection. Now, the next question, sorry about that. My daughter came in asking me about can she have this, can she have that? She keeps interrupting me at the moment when I'm doing these. Explain why aluminium window frames do not corrode after they are made. So, aluminium window frames don't need to be protected. What actually happens with aluminium? Aluminium's quite reactive. It's more reactive than iron. However, aluminium reacts with oxygen to form aluminium oxide. However, unlike rust, this is a strong, unreactive barrier. So, um, protects the aluminium from reacting. So essentially what happens, not all oxides, metal oxides are the same. Iron oxide, hydrated iron oxide, i.e. rust, is orange and flaky. You don't want your iron to become iron oxide because it's orange and flaky and it's brittle and it makes holes in things. So it's no good on your bridge, your car, your bike. But aluminium reacts with oxygen and forms aluminium oxide. The thing is, it very quickly reacts with oxygen in the air to form a white, kind of silvery white coating of aluminium oxide above the iron. Now, it just so happens that unlike rust, aluminium oxide is strong and unreactive. So it actually protects the rest of the aluminium from reacting with anything. So it's actually quite good. Aluminium oxide is not a bad thing, unlike iron, hydrated iron oxide. Anyway, that's the end of that question. Let's bust out the next question. Okay, question 5. This question is about the combustion of fuel. Some central heating boilers use wood as a fuel. Suggest 2 reasons why wood is more sustainable than natural gas as a fuel for central heating boilers. So, 2 reasons why wood is more sustainable. Um, Wood is renewable, um, as you can plant more trees, whereas natural gas is non-renewable, um, comes from crude oil. Okay, and natural gas, the wood does not need much processing, right? So if you want to make wood ready for burning, you just chop your tree down and you can burn it, basically. The wood doesn't need much processing. What we can say is natural gas has to be extracted by fractional distillation. Fraction or distillation. I mean, first of all, we could say crude oil has to be extracted from the ground. So let's say crude oil has to be extracted um, from seabed or underground. Um, Then natural gas has to be, I shouldn't say extracted, it's already been extracted, sucked up from the ground. It has to be separated by fractional distillation. Um, these processes are high energy demand. So basically, I haven't really worded that very well, but they use a lot of energy. So when you get wood, you just grow it, you chop it down, and you can plant another tree so it will never run out. Crude oil has to be extracted from the seabed or underground, and then it has to be separated by fractional distillation before you can even use that natural gas. You have to get it out of the oil. The other thing to remind ourselves, which might kind of already be when we talked about wood is renewable, is that natural gas natural gas is finite and will run out. So essentially, because it's non-renewable, it's going to run out. It's obviously harder to get hold of and extract, more difficult, and it's also going to run out. There we go. I mean, both of them release carbon dioxide and water. When you burn them, you would probably say that you get more pollutants from natural gas. You might get some sulfur dioxide and some other things when you burn it. Okay, let's move on. Natural gas is mainly methane. When methane burns, it can produce carbon monoxide, sorry, and carbon dioxide. Explain the process by which carbon monoxide can be produced when methane is burned. And it's worth 2 marks. You just need to think of 2 key words. Why don't you press pause on the video, have a go, and then unpause and I'll explain it. All right, I'm going to go through it. So explain the process of how carbon monoxide is formed when methane is burned. So carbon monoxide will not normally form. Normally, you're not going to get carbon monoxide. You're normally going to get carbon dioxide. Why do we get carbon monoxide sometimes? And the idea, you should know the name of this process, incomplete combustion. I'm better off writing a sentence and saying carbon monoxide forms during incomplete combustion. Now, what is incomplete combustion? This is when there is a lack or insufficient oxygen, a lack of oxygen or not enough oxygen. You might have some oxygen, but not enough. And it means that the methane doesn't completely burn as fully as it can, and it forms carbon monoxide. Now we're going to get down here. You can try this. You've only got to write a couple of numbers on a bit of paper. Balance the equation for the combustion of methane to produce carbon monoxide. Now, these, you can pause the video and have a go, folks. Make your revision active. Okay, what I'm going to do is go through. Now, all you do with these fuels, so check out this. This is the fuel. They're normally hydrocarbons, CH4. You can have O's and other things attached. Then they're not hydrocarbons, but they can still be fuels. You know, in Brazil and South America, they use alcohols like ethanol, C2H5, OH as a fuel. So anywho, when you burn this, you check how many carbons are here, and that tells you how many carbon monoxides or carbon dioxides, if it was complete combustion, you'd need. So I only need one of these. Do I need to write one? No, but I'm going to write one there, but you don't need to write one because there's only one. Now, there are 4 hydrogens and each water molecule requires 2. So all you do is you look at how many hydrogens they are, and then you half that amount and put that in front of the water. So there's going to be 2 waters, and because it's methane, 1 carbon monoxide, 2 waters. Now what you do, the final step, is you add up how many oxygens, there are on the right, and then you just put that number, you make sure that it's balanced by putting that here. So I've got 1 oxygen over here. So I've got 1 oxygen here. And over here, I've got 2 times 1. I've got 2 oxygens over here. And that leaves me with 3 oxygens. And I know what you're thinking. There's 2 oxygens there. If I put a 2 there, it's going to be 4. If I put a 1 there, it's going to be 2. How do you show 3? Well, what we're going to do, we're going to put a 1.5 oxygens. Now, you might say, so I'm not sure I'm allowed to do that. You can put 1.5 if you like, or 1.5 oxygen. You can. You are allowed only when dealing with fuels in organic chemistry to do like use halves. You can't use that in other equations, but just in fuels, hydrocarbons, you can use halves. Now, if you're uncomfortable with that, just multiply everything by 2, and that means you're going to put a 2 there instead of 1.5. that will become 3. I like to use the halves because then I don't have to do this. And then I'm going to multiply everything by 2. So I'm going to times that to 2. And then we're going to come along here and turn the H2O to 4. So that is a balanced equation. But again, I just write the version where I don't need to double the fuel, where I'm going to use 1.5. But I'm comfortable with that. If you're uncomfortable with that, use this version where you go through, you balance it with 1.5, and then you say, I'm not comfortable with that, and you times it all by 2. But make sure you double everything. All right, let's move on. Oh gosh, I'm ticking the whole page. Come on. Right. 5.4, and then it's the end of this question. Propane burns to form carbon dioxide and water. The equation for the reaction is C3H8 plus 5O2 goes to 3CO2 plus 4H2O. 3.6 decimeters of carbon dioxide is produced when a sample of propane is burned in 7.25 decimeters of oxygen. Calculate the volume of unreacted oxygen. I'll be honest with you, they missed something out that is vital in this question. That was a big mistake by the exam board. They should have, for technicality's sake, they should have said at room temperature and pressure, because at room temperature and pressure, the volumes of oxygen are equivalent to the moles. So essentially, at room temp and pressure, 1 mole of oxygen, 1 mole of any gas is equal to 24 decimeters. Now, I can transfer this into moles if I want, but there's no point. What I'm going to do here, 3.6 carbon dioxide is produced when a sample of propane is burned. So I know I've got 3.6 of the carbon dioxide in 7.25 decimeters of oxygen. Calculate the unreacted oxygen. Okay. So what we want to do is go, well, how much is that going to use up? 4 marks. Yeah, we can do this. There's a number of ways we can do this. So not all of the oxygen has reacted. If all of the oxygen had reacted, it's in a ratio. Check out these numbers. These are called the ratio numbers. If all of the oxygen have reacted, it's in a 5:3 ratio. So if I had 7.25 of oxygen, what you do when you're using the ratio, you divide by the first number and times by the second in the direction we're going. So we're going from here to here. Sometimes they ask questions where we're going back that way. So if I'm going from here to here, I'd go divide by 5 equals that, times by 3 equals that. I should have made 4.35 moles of carbon dioxide, but we didn't. So why is that? Well, there wasn't enough of this propane, evidently. So what we're going to do, forget all of that. We're going back this way. We want to work out how much oxygen got used. So we had 3.6 of that. So we're going to go 3.6 decimeters. We're going to divide by 3. And that gives me 1.2, and then we're going to times by 5, and that gives me 6 decimeters. So 3.6 of carbon dioxide would use up 6 decimeters of oxygen, and that's because you divide by 3 times by 5. So you follow the ratio in the direction you're going to see how much would get used up or produced. So if I had 3.6 of carbon dioxide and I was going this way, the maximum I can make is 6 decimeters of oxygen. So 3.6 carbon dioxide came from 6 decimeters of oxygen. How much is left over? We're going to go 7.25 minus 6 equals 1.25 decimeters. Now I have to say that question's a little bit tricky. And there we go. A lot of marks for only a few calculations, but unless you're really comfortable with using ratios and comfortable with the fact that the gas, when you've got gases at room temperature and pressure, you can just use the ratios like you would with moles. If we wanted, we could have divided by 24 and turned into moles and then worked our way back, but there's no point. Okay. Figure 8 shows a surfer on a surfboard. Surfboards are made from polymers. Surfboards have a polystyrene core and an outer skin. As you can see, this surfer's riding a wave. Figure 6 shows the displayed structural formula of polystyrene. Oh my days. Figure 7 shows an incomplete display structural formula of the monomer styrene. So we want the monomer, the small molecule that makes the polymer. Can you complete this? Can you add the relevant bits in to get 2 marks? Why don't you pause the video, see if you can scribble out the structure of the monomer? All right, I'm going to go through it. So we're looking at the monomer. Remember, monomers are the tiny little molecules that can be added together to make a big long chain called a polymer. We have addition polymerization, in which you need a double bond. And this, of course, is an addition polymer. Most plastics come from addition polymerization. So you want to return the double bond to the middle because they're alkenes. And you can put a little n outside to show any number, and then just put the other covalent bonds in, and that's going to get you both of the marks. Let's go down to 6.2. The outer skin of the surfboard contains a polyester. The 2 monomers A and B are needed to make the polyester. Figure 8 shows how these 2 monomers are represented. We've got monomer A here with 2 OHs, 1 OH on each side of the square there, and we've got COOH on either side of the square for monomer B. Now, the first question is name the functional group in monomer B. So why don't you pause the video, see if you can come up with a name. Now, monomer A is an alcohol. It's a diol, meaning 2 O's, and the other one is a dicarboxylic acid, 2 carboxylic acids. Guess what? COOH is the functional group for carboxylic acids. It contains a carbon with a double bond to an O, and as I'm going to draw here, and it contains an O and H, an alcohol group as well. Okay, 6.3. Monomers A and B join together to produce a polyester and a small molecule. Name the small molecule. So this is going to take a little bit of drawing. So I'm going to draw these together for you. So I'm going to use a rectangle, as they have in this question, to represent lots of carbons and hydrogens. And then essentially we've got the carboxylic acid and the OH group on the alcohol. They react together, removing 1 OH, doesn't matter which one you remove it from, and an H from the other one. And then you join the 2 ends up. So the carboxylic acid bit joins with the alcohol bit, and they join together. And you just have to make sure you remove an OH. Now that's a diester. Polyester, you've got to remember to remove 2 H2Os, sorry, 2 H2Os for a polyester. This is just, so the water molecule is what's removed. God, I'm waffling. Why does this type of polyester melt when it's heated? So polyesters are big long chains of plastics, and all polymers have something called cross links or bonding, intermolecular bonding between the molecules. Now these are weak. Generally these are weak forces. They're not as strong as covalent bonds or ionic bonds, these cross links. They're weak intermolecular forces, and a polyester has only weak intermolecular forces which do not require a lot of energy to break. Hence, it's easy to melt. A bit like simple covalent molecules. These are large molecules, but they are simple molecules with only weak intermolecular forces. They just happen to be large ones, so their intermolecular forces are stronger than, say, carbon dioxide and etc. Other simple molecules. Yeah, so there we go. Weak intermolecular forces between the molecules, or you can say no cross links, easy, doesn't require a lot of energy to break, hence that's why they melt. The outer skin of surfboards is a composite material. The composite material contains glass fiber surrounded by a polyester. Draw one line from the material to description of that material. It's worth 2 marks. Why don't you pause the video, see if you can work it out. Alrighty then. Glass fibers are actually a type of reinforcement. They're going to be like long glass strings that are for strength, and they're going to be coated in a layer of plastic that binds it all together. Now, we call a binding substance a matrix, and a matrix holds everything together in chemistry. Of course, the polypeptide is a type of protein that is not the polyester, but I imagine some people went for that one. So the matrix is like the plastic coat. Like if you imagine a wire has got a plastic covering around it. That's the polyester, and then the metal inside which is obviously conducting electricity, is separate to that. Anywho, right, let's get on. 6.6. The outer skin makes the surfboard more expensive. What could be two reasons for the company spending more money on making these surfboards? That's not good for them to make it more expensive, right? However, this outer covering makes it last longer. It doesn't crack or break or weather as quickly, so it's more durable and stronger, less likely to snap when you're surfing. You don't want that when a shark comes up behind you. Dun, 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 dun. Right, 7.1. A large amount of aluminium sulfate was aluminium. God, I can't speak. A large amount of aluminium sulfate was accidentally added to drinking water supply at a water treatment works. Describe a test to show that the drinking water contained Al3 plus aluminium ions. Give the result of the test. Pause the video, see if you can write it down, folks. Right, I'm going to go through the answers. So with aluminium, you could try and do a flame test, but it doesn't really give off a distinct color flame aluminium, so you won't be able to distinguish it from other metal ions. So what you need to do is, when you can't use the flame test for whatever reason, you add sodium hydroxide solution, NaOH with AQ in brackets. And what you get with aluminium is a white precipitate. Now, you also get a white precipitate with magnesium ions and calcium ions. So it's like, oh, which one is it? Well, if you keep adding the sodium hydroxide until it's in excess, the aluminium hydroxide precipitate, which is white, will dissolve. So first it goes white, and then you keep adding the sodium hydroxide until it's in excess, and then the white dissolves and it goes colorless again. And here we go. So it goes colorless, white, colorless. 7.2, describe a test to show that drinking water contains sulfate ions. Give the result of the test. Now, the sulfate ion is the SO42 minus ion. It's a negative ion and an anion. And the test for it is to add barium chloride solution. Now, the barium, the Ba2 plus ion, will react with the SO42 minus ion to form BaSO4, barium sulfate. Now, barium sulfate is insoluble. So it's not like barium chloride, which is a colorless solution. Barium sulfate is insoluble and it's white. So what you're going to see is a white precipitate. Now, it's very important that you also say you're going to add an acid to get rid of any impurities. And so you're adding barium chloride, but you're going to add hydrochloric acid. Don't say you're going to add sulfuric acid, because that would add sulfate ions and give you a positive test result. You have to add hydrochloric acid with your barium chloride. It will get rid of any carbonates or other impurities. You'll get a white precipitate formed, and that's really your answer. BaSO4, solid or white precipitate of barium sulfate. Okay, 7.3, plan an investigation to find the total mass of dissolved solids in 100 centimeter cubed sample of drinking water. Your investigation should produce valid results. Now, what is valid results? It means it's fair. You've done a fair test. We don't use the word fair test now in GCSE. They used to once upon a time, but that's been kicked out many years ago. So valid results mean you've controlled any variables that could affect it. So the first thing to do is measure the mass of an empty container that you're going to weigh things in and put things in. So you know the mass of that container. So it could be like an empty beaker, a crucible, a little dish, whatever. You're then going to add 100 centimeter cubed of the drinking water to the container, reweigh and subtract, so you know how much the water weighs, how much the container weighs. Okay. Why is that important? Well, you're going to see later on, because if we know the container weighs a certain amount, then when we evaporate all the water and reweigh it, we'll know exactly how much salt or solids have been left behind in the container. So let's make up a number. Let's say our empty beaker weighed 52 grams. Okay. Then we're going to fill it with 100 centimeter cubed of water. Maybe, or generally, water should be 1 gram. It has a density of 1, so 1 gram per centimeter cubed. So we can say that 100 centimeter cubed of water would make it weigh 152 grams. Now we're going to heat the water until we evaporate all the water. How do you know all the water is gone? You could say, well, look at it. That's not good enough in science. We need to heat it until a constant mass. This means you heat it, weigh it, heat it, weigh it. Once you see all the water's gone, you still heat it, weigh it every 5 minutes until you get 2 or 3 measurements where the mass stays the same. Then you know no more water's coming off and all the water has evaporated. Now reweigh the beaker once it has cooled down, of course, and we'll see, look, my beaker is 56 grams. Well, originally it was 52. Now my empty beaker weighs 56. It means I've got 4 grams, 56 minus 52, of solid left behind. And that's how you work it out. Now, you might want to repeat this 3 times using repeat 3 times, using 100 centimeter cubed of water each time, and then calculate a mean, subtract any anomalous results, etc. Anyway, this will get you all the 4 marks. You don't really need the diagrams, you don't need the numbers. That's just an explanation to allow you to see how what we would actually do. Okay, Titan is a moon of the planet Saturn. We're on question 8. Table 3 shows the percentages of gases in the atmosphere of Titan. We've got nitrogen, methane, and other gases. 90 something 8.4 or whatever that is. Nitrogen 1.4, methane what 0.2 other gases. Some scientists think that living organisms could have evolved on Titan. Explain why these organisms could not have evolved in the same way that that life is thought to have evolved on Earth. Use table 3. It's worth 3 marks. So here's my little diagram of Saturn, and here with the little t is Titan. A moon orbits a planet. Obviously, the gravitational pull of Saturn pulls Titan around along with loads of other moons. But why is it, looking at that atmosphere, Titan, life, if it's evolved on Titan, could not have evolved in the same way as life on Earth? And when they use the word explain, you have to use science. And so you have to use your science knowledge. What is missing from those gases that we need on Earth for life? And there's 2 main gases you can talk about here. There's no carbon dioxide, right? By the way, you should have paused the video and had a go, but if you haven't, you could do that now. There should be some CO2, right? Why? Because CO2 is needed for photosynthesis. That's how all the plant life grows on Earth, by photosynthesis. Absorbs the CO2 and it produces foods, sugars, and resources for the animals. So, and of course, photosynthesis then produces oxygen, which oxygenates the atmosphere and allows animals and plants to respire. So you need oxygen and carbon dioxide for life to have evolved in the same way as it has on Earth. So we want to point out there's no CO2, so no photosynthesis, and there's no oxygen for respiration for animals or plants. So life cannot evolve in the same way as on the Earth, because we're missing those 2 vital gases. I mean, the most important one's CO2, because then you get photosynthesis, which produces oxygen. All right, let's lick on to 8.2, peeps. Saturn has other moons. The other moons of Saturn have no atmosphere. Titan is warmer than the other moons of Saturn because its atmosphere contains greenhouse gas methane, the greenhouse gas methane. Explain how the greenhouse gas keeps Titan warmer than the other moons of Saturn. Why don't you press pause on the video and have a go? Okay, I'm going to show you how this works. So bear with me while I bust out my level 4 GCSE art. Hokey cokily. So once again, I bust out the sun with Saturn and Titan going around it, but we're more interested in just the sun shining on Titan and how the greenhouse effect works. And essentially, this is asked in the context of Titan. It's just them being fancy. They could have asked you this about the Earth, which they normally would. So we have greenhouse gases in the atmosphere. That's my dashed line around this pink object, which is Titan. These greenhouse gases, such as methane, which is the greenhouse gas on Titan. Now we have ultraviolet light. Notice I've done a squiggly yellow line. That represents the ultraviolet light from the sun. Now, if you don't want to say ultraviolet light, you can call it short wave radiation. Why is it short wavelength? Well, they're very close together, high frequency. Short waves have high energy. Notice some of the energy is absorbed by the planet and warms it up. This means the energy that's reflected, the wave that's reflected, has a longer wavelength. We call this IR, infrared radiation, and that is reflected, bounced off the surface of the planet. So short wave radiation can punch through and penetrate the atmosphere because it's got high energy and very short wavelengths. And this ultraviolet is an example of a short wavelength radiation the sun releases, penetrates the atmosphere, hits the surface of the Earth, and warms the planet up. Now, if there was no atmosphere, it would just bounce off the Earth as long wave radio waves or infrared radiation, and it would just go off into outer space. However, this radiation, it's been converted into infrared because it's lost some energy, so the wavelength gets longer. And therefore, this longer wavelength is not able to penetrate and get out of the atmosphere into outer space. And it is absorbed by the greenhouse gases such as methane or carbon dioxide. In this case, it's Titan, so it's methane. And this warms up the planet. And we call that global warming or the greenhouse effect. And that's how it works on the Earth as well. But the majority of the greenhouse gas is carbon dioxide on the Earth, the main greenhouse gas. And so you're really seeing most of the energy is absorbed into the planet. Now, if it was outer space, look at my drawing on the right here, that long wave radio waves, sorry, infrared radiation, IR, would just escape to outer space. And the planet, it'd still get warm from the sun in the first blast from the ultraviolet. But when it turns to IR, it would just escape to space. When you have greenhouse gases, it's absorbed into the atmosphere and re-warms the planet up. The atmosphere of Titan contains small amounts of propane. Describe a test to show that propane is an unsaturated hydrocarbon. Give the result of the test. Right, you're going to pause the video and have a go at this one. Hydrocarbons are made of carbon and hydrogen. Unsaturated means it has a double bond, and propane has 3 carbon atoms. So this is just doing a bit extra. You don't need any of this to score the marks in this question, but that's how you would draw propene. Okay, it's got 3 carbons, it's got 6 hydrogens, and it's got a double bond. Now along comes your bromine. Now it can't add to an alkane like propane, but there is space for it to add here. And when it adds, the double bond has to break because each carbon's in group 4, it has 4 electrons in the outer shell. It cannot have more than 4 bonds. So the double bond has to go and the bromine adds on. Now, bromine water is orange in color. Bromine itself is a red liquid, but bromine water is lighter, it's orange in color, and when it adds on to an alkene it goes colorless. So it's a great test for the double bond or for alkenes. Right, we're on question 9, peeps. Don't forget to hit the like. Some students investigated the rate of decomposition of hydrogen peroxide, H2O2. The equation for the reaction is 2H2O2 goes to 2H2O, that's water, and oxygen gas. The catalyst for the reaction is manganese dioxide. Describe a test to identify the gas that is produced in the reaction. Give the result of the test. So it's asking you what is the test for oxygen. You could pause the video and have a go if you want, or you could just watch me go through the answers. So you're going to use the glowing splint. You light a piece of wood in the Bunsen burner, you blow it out like that, and then you put it near where the oxygen gas is coming out and it relights. So relights a glowing splint. A student A investigated the effect of particle size of manganese dioxide on the rate of reaction. This is the method used. Measure 25 centimeter cubed at 0.3 mole per decimeter hydrogen peroxide solution in a conical flask. Add a spatula or fine manganese dioxide powder to the conical flask. Measure the volume of the gas produced every minute for 10 minutes. Repeat steps 1 to 3 with some coarse manganese dioxide lumps. The method student A used did not give valid results. What 2 improvements could student A make to the method to give valid results? It's worth 2 marks. What does valid results mean? Valid means you have controlled the variables that affect your independent variable now, or that affect your experiment. So we'll change the variable. Basically, what am I even waffling about? We need to think about what 4 things affect the rate of reaction, and you should know these off by heart. You've put them on a revision card, so you can change the rate of reaction using temperature, surface area, concentration, or pressure. Now, they have not controlled all of these things, but they've controlled some. So we have to select which one should they control. Now, they shouldn't control the surface area because that's what they're changing, the effect of particle size. So that one's not relevant. But when we read through these answers, place the conical flask in a water bath at a constant temp. Yes, they should use a constant temperature because they're investigating surface area. Use 0.05 mole. That means basically the concentration. They used 0.3. Look here, they used 0.3 mole. They already controlled the conch, so that's not going to be one of the answers. That was controlled and was a control variable. Was there anything else they missed out? They said add a spatula of manganese dioxide. That's rubbish. They should have used the same amount of catalyst each time, and they didn't. They just used a rough heap on a spatula. So those are the 2 answers. Okay, student B used a method which gave valid results. Figure 9 shows student B's results. Here's figure 9. Volume of gas in centimeter cubed on the y-axis and time in minutes on the bottom there. We can see we've got fine manganese dioxide powder and coarse manganese dioxide lumps. So they're investigating surface area here. 9.3 determine the mean rate of reaction in centimeter cube per second between 2 and 4 minutes for coarse manganese dioxide lumps. Give your answer to 2 sig fig. Use data from figure 9. Grab your calculator, pause the video and have a go, folks. Okay, determine the mean rate of reaction. Yeah, so I'm going to redo here. Right, I just lost all my stuff. So my screen went my internet glitch and I just lost it all. Let's do it again. Right, so we've got to do this to two significant figures and between 2 and 4 minutes. So draw your line up and finally bring it over. So draw the line up between 2 and 4 to the solid black line, which is the coarse lumps. Then draw it over to the y-axis. Now you need to work out what these numbers are, and you're going to have to work out what the scale is. So you can see it goes 0, 10, 10, 20, so 10 centimeter cubed at a time with 5 baby squares. Each baby square is worth 2 centimeter cubed. So if we go here, this is going to be 45 because it's right in the middle of one of those baby squares. That's very hard to see on the screen, but it is. And over here, you're going to lose 1 mark if you get this wrong. Even if you get error carried forward. And then it's 56 on the next one. So we're going to go 56 minus 45. There was an increase in 11 centimeter cubed, and it took 2 minutes. So if you did 11 divided by 2, that's going to be 5.5 centimeter cubed per minute. But they want the question in seconds. So we're going to do 120 seconds because 2 minutes times 60 is 120 seconds. We do 11 divided by 120, and we're going to get 0.0916. Wrote that in the wrong way. The 6 is bigger than 5. They want it to 2 sig figs, so we're going to raise that 1 to 2. So the answer is going to be 0.092 because you don't include the zeros, but you're going to put the first 2 proper numbers, and that's going to be 91 or 92, and you're going to go 92 because the 6 was bigger. So 0.092. Hydrogen peroxide molecules must collide with manganese dioxide particles for catalysis to take place. Student B repeated the experiment with coarse lumps of manganese dioxide. Student B used the same volume, 0.2 mole per decimeter hydrogen peroxide, instead of a 0.3 mole. So basically they've changed the concentration, and that means that we have 1/3 less particles. Sketch on figure 9 the curve you would see. So we need to sketch on here the curve we'd see. Now we've got 1/3 less particles because they're doing a conch of 0. What are we doing a conch of? We're doing a conch of 0.2 instead of 0.3. So I want to go 2/3 of the way up here. So this would be 0.3. If you divided this, it's 6 centimeters up or 6 squares up. So 0.3 is the 6. 0.2 would be 4 and 0.1 would be just 2 squares up. So you basically, to get all of the marks here, you got to work. We're going to produce less gases. We have less reactants with 0.2 instead of 0.3. So it's going to be 2/3 less. No, it's not going to be 2/3 less. It's going to be 1/3 less. Sorry, I just glitched out there. Probably the AQA exam board trying to interfere with my video so that you can't get the A star. All right, here we go. So if you look there, that's where I'd expect 0.2 to finish here. So 1/3 less, because 0.2 is 1/3 less than 0.3. So we're going to finish about there. And you're going to get 2 marks, maybe 3 marks for that one. Okay. Right, let's zing in. The rate of reaction is different when manganese dioxide is used as a fine powder rather than coarse lumps. So when you might want to pause and have a go at this. Why is it that fine powder reacts faster? Well, you're increasing the surface area, which means more collisions between the reactants. There's more available particles to react when you use a fine powder. There's more surface for contact and more collisions. So you're going to get more collisions per second because you have more available particles. Right, 10. The question is about reversible reactions and equilibrium. Hydrogen is used to produce ammonia in the Haber process. Hydrogen is made in 2 stages. Stage 1 is the reaction of methane and steam to produce carbon monoxide and hydrogen. The equation for the reaction is CH4 plus H2O, reversible symbol CO for carbon monoxide plus H2 for hydrogen. And we've got 3 lots of the H2. Calculate the atom economy for the formation of hydrogen in stage 1. Pause the video, have a go, folks. Well, I'm going to go through it. You're going to do the useful product, total MR of the useful products over the total reactants, okay, times 100. And so all you're going to do is work out the useful product is hydrogen. 3 times H2 is 6, and then over 34, which is the total if we add up methane and water, and we're going to times by 100, and you're going to get 17.647. I would round that up to 17.65, or you could just put that as 17. Oh, put a 5 there, you idiot. There we go. Okay, there we go. Yeah, I'm leaving it like that. All right, 10.2. Explain why a low pressure is used in stage 1. Give your answer in terms of the equilibrium. You might want to pause the video, have a go at this one. Why do they use a low pressure? Look on the left-hand side, we've got 2 gas molecules. On the right-hand side of the equilibrium, on the forward side, we have 4 gas molecules. Now, you can call about backwards, forwards, left, right, or yeah, you get the idea, right? I'm going to call it the right and left. So there are more gas molecules on the right hand side. So lowering the pressure causes the equilibrium to shift to the right hand side. And why is that? Because Le Chatelier says it will always do the opposite. So if you lower the pressure, Le Chatelier says the reaction will try to shift the equilibrium in the direction of more pressure to change, to oppose your change, to go against what you did. And the high pressure side is the right side because there's more gas molecules. Now for this one, they're saying, what's the effect of increasing pressure on this reaction? We'll have a little look. How many particles are on each side? There's 2 gas on either side, on the left and the right. Well, what does that mean? That means that changing the pressure will have no effect on the equilibrium. It will have an effect on the rate of reaction, however, but they've specifically asked about equilibrium. So watch out for if they say rate of reaction or equilibrium, because you get 2 different answers. Okay. Figure 10 shows the percentage yield of ammonia produced at different temperatures and pressures in the Haber process. We've got this graph here. A student suggested that a temperature of 350 and a pressure of 285 atmospheres could be used instead of those in the Haber process. Determine how many times greater the percentage yield of ammonia obtained would be. So they've told us it's going to be bigger. This is just a reading the graph technique. So we want to start off with the 450 degrees temperature and 200 atmospheres. Let's work out what the original pressure in the Haber process, yield is. So we go across with this arrow and we find that if you go up to that line, which is the 450 line from 200 atmospheres, you get a 28% yield. Okay, lovely, bubbly. Now let's look at the new temperature and pressure. So if we lowered the if we increased the pressure to 285 and we hit a 350 temperature and we draw the line across, look at the big change in the yield. The yield goes from 28% up to, what's that, 63, I believe, because I think each one of these squares is worth 2. Yeah, each square is worth 2%. So that is going to be 63%. So what is that an increase? Well, how many times greater is it? Well, I would do 63 divided by 28 to see how many 28s you'd fit in there, and it's 2.25 times greater. So it does make you ask the question, why is the Haber process done at 450 and 200 if you can get a much better yield? More than double better yield. Well, we're going to come to the reason why they don't actually use it. Pressure of 285 is not used. Give one reason why they don't use that higher pressure, even though you get a better yield. Well, high pressure is expensive. It's dangerous because you can get an explosion with high pressure. You need thick steel walls on your reaction vessel, your big container. You'd need thick steel walls to stop it exploding. Steel costs lots of money. You need lots of safety equipment as well for your workers, and that's the reason. Right, how does figure 10 show the Ford reaction is exothermic? So how do we know that this is a heat giving out reaction? When they use a lower temperature, what happens? When they use 350, what happened to the yield? We got a higher yield when they used a lower temperature, which proves that the equilibrium is shifting to the right, to the hotter side, which means it's exothermic. Okay, so that's a little bit complicated. World production of ammonia is now about 30 times greater than it was in 1950. Suggests why the demand for ammonia has increased. Okay, ammonia is used in fertilizers, so you need to know that off by heart. It's used to make ammonium nitrate and things like that. The human population has increased, therefore we need more food, therefore we need to use more fertilizers on the farms, agriculture. And that's the answer. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. I'll catch you lot on the next video. Let's smash the GCSE.
You're still here? It's over.